Okay, let's talk a little bit about image quality. So, we have two big determiners of how we think about resolution for these pictures, right? And the resolution is the amount of detail that we can see on an image. So the big enemy of resolution is probably going to be noise, right? So we'll talk about that next. But spatial resolution is going to increase as we decrease things like motion blur or any kind of problems with the geometry, blur related to focal spot size and things like that. Contrast resolution is going to improve as we're able to accurately record what's happening in terms of the way the pixels are working and stuff like that. So the other thing that is kind of a problem, so what it talks about in our textbook is that this contrast resolution is going to deal with the visibility of that detail, right? So the enemy of both of these is noise, and noise is going to be any kind of random fluctuation in the values that we've got on the image receptor, okay? So we're going to break more. Again, noise is given as this random fluctuation, right? Where the machine, we've told the machine should be seeing, so it's got like a bank of pixels right here, and due to attenuation and the way that the beam is passing through the patient's body, this pixel here should be darkened, right? It should have been darkened by a photon interaction at the level of the image receptor, right? But let's say perhaps because of Compton scatter or something, instead of darkening that pixel, it darkens this pixel, right? We would now call that noise, right? It's influenced our image in a way that's not actually accurate to the object that we're trying to record. So, different ways that we talk about noise include the graininess of film. Again, this is just a film factor. So, back in the day when we were using film, they had sensitivity specs all throughout the film. And if there were not enough sensitivity specs kind of distributed through the film to give it an appropriate amount of resolution, it would appear kind of grainy, right? The same thing could happen if, for example, we're x-raying a patient. So here's my patient, right? And, oh my goodness. X-rays pass through the patient's body, right? But I have not created a sufficient number of x-rays to fully expose the radiographic film, right? So now I would have graininess related to there not being sufficient amount of darkening on the image, right? The way that we talk about that in terms of digital imaging largely is quantum model, right? And this is one of the reasons why we have things like dose creep. So put quantum model at kind of the top of your priority for aspects of noise to understand, okay? Because what happens in a digital system, if there's not enough of a remnant beam, right? So we've got the x-rays we produced on this side, right? And on the second side we have the remnant beam. That's the x-rays that are exiting the patient, right? If there's not sufficient numbers of x-rays exiting the patient, the image that we're going to get is going to be very snowy looking. And that snowiness we're going to call quantum model. What's happened from the computer's point of view is it got some kind of signal, but it also got a whole lot of noise. And there wasn't enough signal to make a clear image. Another thing that can affect noise is scatter radiation. So these are events where we had, as I mentioned earlier, a photon that exits at a funny angle, right? So there should have been darkening right here on my image receptor. Instead, there was darkening up here on my image receptor. Okay? So scatter can contribute to some of the noise as well. And we've got things that we're going to put into place to reduce that impact on the image contrast, largely grids. We're talking about grids and buckies and stuff like that. So these still apply. One of the things that's kind of interesting about moving from film to digital systems is a lot of these rules of radiographic quality are still in full effect. So fast image receptors have high noise and low spatial resolution and contrast resolution. High spatial resolution and contrast resolution require low noise and slower imaging receptors. Okay? So low noise accompanies a slow imaging receptor with high spatial resolution and contrast resolution. There's a lot of different ways that we can think about this graphically, right? But I want us to just kind of think in particular about that word quality, right? Where earlier in our textbook it tells us that it is not easy to precisely define this term, right? But one of the ways that our textbook is going to ask us to think about quality has to do with an H and D curve or an S curve, right? So I'm going to draw these in really exaggerated form. But I have one that's really steep here on the left and one that's very, I shouldn't say not so steep, but it's less steep on the right, okay? These curves indicate the way that an image receptor is receiving the signal, okay? So at the toe side of the curve, right here, at this toe level, this is when it starts to receive the signal, okay? So it starts to receive its X-ray signal. It starts to register that signal as it goes up the curve, and then its ability to register the signal kind of goes away. So we have this area here called a shoulder, right? So this is our shoulder to an H and D curve. This here is the slope, right? If it's a fast image receptor, right, the distance along this y-axis, this y-axis right here, the distance from the toe to the shoulder is going to be pretty short. It's a fast image receptor, right? It started getting a signal when it shot up that slope, and then it stopped receiving the signal, right? So it's going to be high contrast. It has a short latitude, right? And we'll unpack that some, but basically the amount of information it can receive has been lessened by how receptive it is. Versus this one, if I measure from here to here along this axis, I would have a wide latitude, right? This has a wide latitude. So it starts getting a signal here, it receives, and the signal starts to fall off, right? So again, it's not going to be a really high contrast thing, and it's going to be slower, right? The way it's receiving the signal is going to be slower. It's going to take it longer to get to that shoulder. This is the film way of talking about this. Interestingly, in living in a digital world, the computers have kind of rewritten the rules a little bit. So we still get something like a toe, right? And that's that area where we would see some quantum model. It starts to receive. I'm going to draw right over the images here, so bear with me. It starts to receive its signal here at the toe, but it just keeps on going, right? This is what dose creep is kind of graphically. It doesn't have a shoulder. A digital system will just keep on receiving. It'll keep on receiving. So without really implicitly saying all of that, the technologists figured this out. The technologists figured out that if I underexpose it, I don't get a picture. but there's no way to overexpose it. There's no way to overexpose this image. Back when we still had the film processor working, I'll see if I have these images in my office. I might. I did a hand x-ray on the old film system. I did a hand x-ray at 2.5 mass and 250 mass. Right? 2.5 mass and 100 times that. 2.5 mass was sufficient mass to get a good hand x-ray on a film system. 250 mass, 100 times that, totally burned it out. So you'll hear techs talk about burning it out. That's what they mean. I burned the film. The film was overexposed. There's no way I couldn't do anything with that film to get any information out of it. It's toast. Like, it's just good to be thrown in a barrel somewhere and they'll recover the silver or whatever from it. With a digital system, I shot the same thing. I shot 2.5 mass and 250 mass and got the exact same picture. Right? Got the exact same picture. For just this reason. Film has a shoulder, digital does not. Okay, so this is one of the reasons why I stress radiation safety so early on. Film has a shoulder, digital does not have a shoulder. If you're charting like an H&D curve, you can artificially put a shoulder in that, and we'll talk about what that looks like and why we've got computer systems. Yeah.
If everything's going digital, then what's to stop radiographers from just completely overexposing a patient just to security then?
That's a good question. I mean, I would say the only thing that's stopping people is what I would call the code of ethics. That's not ethical. Like, it's just not ethical. Just because you can do something doesn't mean you should. But yeah, there's no, other than professionalism and just the codes of professionalism, there's nothing to deter someone from doing that. In fact, within the workplace, there might even be incentives to doing that. Like, so what we see is, for example, I've heard that at Baptist outpatient, people are fluoroing to position patients and then taking an x-ray or something absurd like that. Like, that's obscene. Like, I can report that to the radiation safety officer. They should know about that. I need to document it some, so that would be the first step. But if we're talking about a whole cultural shift, right, which is what this is, like an entire, like, film has gone away and we have the rise of the machines, right? The computer is now on the scene. We're going through a cultural shift, and so this is one of the ramifications of it. There's good stuff about digital, there's great stuff about digital, but then there's also this. So back in the day, we used to be able to calculate optical density. We could hold this little sensitometer to the film, and it could tell us how dark the film had been darkened in that area. So we would sketch out optical density, and as you can see, it's a logarithm, so that all that means is it has a shoulder and a curve. What we would get would be a slope with a shoulder and a curve, right? It'd be an exponential process. That's all that means. For our lab group today, we are going to interrogate just this question. In a digital system, is there any parallel to this? Is there any way to talk about optical density anymore? Or has digital so altered things that this conversation is now obsolete? If so, what has taken its place? Because we can't get rid of a value like the degree of darkening on an X-ray without something else taking its place. So here again is that characteristic curve as it relates to optical density, right? We can see that as we begin an exposure, we have a large degree of whitening on the image, right? Then it talks about diagnostically useful densities, right? These are all the various shades of gray going from the whitest white to the blackest black. Eventually this curve just falls off because once I've burned the film out, there's no additional information I can get from that film. I've hit the ceiling on it, and it's useless now. It's just a piece of plastic. But between that white place of an undeveloped, unexposed, or an unexposed but developed image, right? Versus the darkest dark of it completely burned out is all the diagnostically useful densities. I talk about them sometimes as the 50 shades of gray, right? Just as a ridiculous mnemonic, but this is diagnostically useful stuff. Geometric factors. So that was all of the image quality factors, right? And I want to stress one thing about the way that we should think about this stuff in terms of structuring our understanding. From the board's point of view, right, you're going to get questions about image quality, image evaluation. And generally those questions can be broken down by those two broad subcategories. Are they talking about technique factors or are they talking about geometric factors? I've not seen a lot of board questions that try to ask both a geometric and technique question. So they're either going to be asking you about the things that contribute to the 50 shades of gray, right? Or they're going to be asking you about the things that contribute to stuff like magnification, distortion, and blur, right? So there's going to, in your mind, you can go ahead to some degree and think about it in terms of technique, if I can spell, oh my goodness, to some degree versus geometry, right? Because that's kind of the way they're going to parse it out. They're going to ask you a question like, this is the technique that you used, right, for acquiring an image. You changed the KVP. What impact is that going to have on the image, the resulting image? That would be a technique question. They might use the exact same factors. Here's the technique that you used. You changed the focal spot size, right? You changed the focal spot size and made compensations for everything else. That's going to be a geometry question. It's asking a question about size, like the actual physical size of the focal spot versus the amount of X-rays that I produce or the energy of the X-rays. Okay? The reason I stress it up front and right now is, I'll be quite honest with you, I haven't been teaching a really long time, but this is an area that trips people up. So I think it's helpful to go ahead and make that distinction now as you're looking at these questions, as you're thinking through this material. Okay, is that asking me about quality related to technique, or is it asking me about quality related to geometry? Geometry shouldn't be a scary word. When I use the word geometry, I'm really just talking about, did this mag things out? Did this distort it? Is there focal spot blur? So I'm not going to be able to show this for anyone who's watching this at home. I won't be able to show you this, but we'll use this whiteboard here. So geometry stuff, right? Magnification. Okay, we learned a magnification formula, right? SID over SOD, SID over SOD. SOD is the source to the object distance. So if I pretend that that projector up there that's making light is a point source of radiation, let me turn the lights down. And I've got this bone that I'm trying to x-ray, right? If I can keep this SID really long and this SOD really long, then I'm not going to have a whole lot of magnification, right? But as I start to decrease that SOD, and so I'm increasing my object, my OID, my object to image distance, I'm decreasing my SID, this thing's going to start to get big, right? So now I have I still have the same SID, the same long SID, but now I have a shorter SOD, source to the object distance. Okay, so I've magnified it, right? That same kind of principle is kind of what's at play when we're talking about distortion, right? I can make this thing appear to be shorter than it is, right? So if I take it and I start to tilt it, I'm shortening it, right? Now the bone looks very short. because of its angulation, right? If I start to mess with this screen and I tilt the screen, I can appear to elongate this bone, right? So bear in mind, if I'm talking about tilting the screen, I'm probably talking about elongation. If I'm going to tilt my image receptor, I'm going to elongate the way this thing looks. If I tilt the anatomy, I will shorten the way it looks. All right? There will probably be a question about that. And a bone appears shorter than it actually is. What technique factor does the tech need to review? They need to look at the way that the part was positioned, right? It's going to make it look shorter. A bone appears longer than what it should on an image. What do they need to do? They need to look at was there an angle on their image receptor, right? So being able to think about geometry and the way it plays a part in this stuff is significant. So in addition to that, we have what we call focal spot blur. And we'll unpack how that works here in just a moment. I think there's a graphic that will be helpful. Oh, here it is. So this magnification factor, if we know, for instance, if I know my magnification, if I've calculated that SID over SOD, I can tell you what my object size will be versus the image size, right? So in addition to questions that ask you to calculate what the magnification is on the image, there might be questions that say, the kidney is actually this size, it appears this size on the radiograph, we can calculate the magnification factor from that. You can also use those formulas interchangeably to figure out other stuff. Like the object size is this. What will its image size be at this SID or this SOD? So some of the things that affect distortion is the thickness of the object itself, right? It's going to play a part in whether or not it's distorted on our image receptor. Again, like I mentioned, the way that the thing was positioned as well as the object's shape. There are some objects that are just difficult to image without there being some distortion on it, right? One case in point is a lateral chest x-ray, right? Due to the object's thickness and its shape, it is very difficult not to have some magnification of the heart, which is a form of distortion, as well as some overlap of the hemodiaphragms, right? Even though we know that one is higher than the other, due to divergence of the beam, they're going to appear to be the same length, right? We actually use that distortion in our favor. Distortion is not always just like a bad thing either. There's times when we might use distortion to be a help. Can anyone think of any times with any techniques or positions that you've learned so far where we use distortion to help us see things better?
I think there's if I'm not mistaken, the tech told me, there's a breathing technique to kind of blur the ribs out to see like the T-spine.
That's good. Yeah, no, certainly we can use things like motion to blur out unimportant anatomy, or they'll do like a wagging jaw image of the dens in the odontoid process. Yeah, do you have one?
Like when you do like obliques, especially for the ribs, you just want to kind of enlarge that. Is that a form of distortion?
Certainly. That's a really good example. Our rib series, oblique rib series, we're definitely using distortion to our advantage. Lateral chest x-ray, as I mentioned. Lateral pretty much anything. Lateral knee. We know when we look at the anatomy of the knee that one side sits a little bit higher than the other, right? But we try to use distortion to make it to where we can see through that joint as easily as possible. Another example of, frankly, of the way we can use distortion in our favor is CT scanning. CT scanning is just going crazy with distortion, right? And then figuring out a way to distort something so much that when we undistort it, we can get additional information from it. So when we talk about CT, we'll talk about radon transformations and Fourier transformations that are dramatically distorting things. But they're distorting them into a totally different kind of image space and then pulling out new information from that image space. So here's another example of a foreshortened object. So this arrow now stands in the place of that femur that I had, right? And then you can see that as it's tilted, the object appears shorter, right? Focal spot blur. So this is one that may not jump out at us right off the bat as being a form of distortion, but it's significant. It definitely has to do with the geometry of how these x-rays are produced. So in addition to something like an anode heel effect, we have the way that the electrons can interact with the anode side of the x-ray tube, right? So we have a cathode boiling off electrons over here, and it's negatively charged, and an anode that's positively charged, operating within a vacuum, right? The problem is when we boil off those electrons, they have to be attracted to a space that has some geometric size to it, right? So it has an actual size. So we can change out what we call the focal spot size. If you look at the old three-phase machine in the honeymoon suite, you can see when you dial in the MA, it's going to change the focal spot size on the MA selector. It'll say like 50S, 25S, and then all of a sudden it'll say 100L, right? The S is a short focal spot, which is generally 0.6 millimeters, and the L is a longer focal spot size, which can vary quite a bit depending on your place. So when it boils off those electrons, right, it's going to strike the anode, and it's going to produce X-rays, but they're going to diverge out at different divergence levels because of this being a slope and it having some distance, right? So now we have some blur, right, at the edges of our image and at the edges of just about any object within the image, related to the size of that focal spot on the anode. Okay? Questions about that? You can see again, not only does the OID or the SOD play into the focal spot size, into magnification, it also can contribute to focal spot blur, right? So something that's further from the image receptor is going to have an increased blur to it, right? It's just going to be blurrier. Okay.